When yesterday arrived, I've read through the program and I've read that I'm in the section of Earth and its inhabitants. I was thinking I should add maybe a motivation why it matters for the inhabitants and for Earth, measuring clouds on top of mountains. And I remember something I've read in a book about mountain forecast, and it gave us these numbers that actually almost 50% of the land surface of its population and of surface runoffs consist of mountains, hills, and plateaus. So it should be quite important to understand how the weather forms on these regions, because I think it has a great effect on all the global models, and if we want to understand how it changes in the future. Because this is just 50% of the population, but I think it has an effect of more people, because hills and mountains also affects the global circulation, storm tracks, moisture transport, etc. So what we are doing is we go up on the mountain and take samples of orographic clouds, which has been in touch with the surface at least once in their lifespan. And a colleague of mine, Gary Lloyd, published a paper in 2015, and he presented results of over 400 orographic clouds. And besides temperature and humidity and everything, one of the key things was he presented ice number concentrations between nothing and over 1,000 per liter. And just to tell you, 1,000 per liter is a very high number. And what is the main issue that they found is that a model they choose to verify those measurements was unable to predict those high ice number concentrations. So they used the weather and forecasting research model and tried to predict it, and it was not only slightly different, it differed up to 3 orders of magnitude. And of course, if it's affecting this model so much, it also affects other models. So we have to understand where those differences come from. So they had 2 ideas. They could increase the ice nuclear particle concentration to, what's up, James? Oh well, so 2 ideas. We could increase the nuclear particle concentration to increase the ice number concentration, or we can include secondary ice processes. But the former idea only led to a prevention of the formation of those mixed phase clouds they usually measure on top of the research station, and including secondary ice processes didn't produce as many splinters as needed to explain the number concentrations. So they came up with an idea to include another secondary ice process, another source, and this should be, they thought, a surface Hoare flux, and adding this theoretical flux to the model was able to so this enabled the model to calculate comparable numbers to the measured numbers. So shortly, what is surface Hoare? Just a little comic. So you have a snow surface, not very unusual, on top of a mountain. And if you have a cloud enclosing this snow surface, and the conditions reach near water vapor saturation, then you get vapor diffusion. And this vapor diffusion leads to the formation of snow surface crystals. And as you can read in a paper from Gallet in 2014, those snow surface crystals are very fragile, so they're composed of needles and interlocking needles, sometimes with some dendrites on them. But as I said, they are very fragile, and small variations in the wind on the surface could cause their fragmentation and removal from the surface. They can enter the cloud, and we measure them at the research station. The only problem is that the results you can read in the paper I just mentioned, they are from Arctic and Antarctic regions, and nobody has ever done any measurements of a surface hoar in alpine regions where we do all our measurements. So this leads to two questions. The first one is, do those hypothesized fluxes really exist? And the second one is, if they exist, do they occur during events, or are they coupled to events when we measure high ice number concentrations? So that's why I had to go back to Switzerland, and we set up a similar system we always used for those 400 cloud events before. So we have a tower and a wing attached to it with a rotator, and besides measurements of temperature, humidity, or the liquid water content, we also measure, of course, the number ice concentration with a 3V CPI, and it's a hybrid of two instruments. The first one is taking the shadow images of particles. So a particle passes a laser and you measure the shadow of the particle, so you get you know how it looks like, and you can calculate the size and the habit of it. And the other one is a high-resolution camera that takes a picture of the images, and you can do the same with it. And the only difference between the systems before and this system is that we use a sonic anemometer right to the inlet of the instrument that measures the number concentrations, because these two things form an eddy covariance system. And yes, so we could apply eddy covariance methodology to investigate we try to find out where the fluxes are coming from, if it's really a surface flux or not. So instead of deriving this equation, I thought I'd just show a very quick comic similar to what Yoshi showed you. I think the density of fluxes talks, and this time is quite high, so I don't have to go into much detail. So we have the mean wind motion going to the right, and in this mean wind we have a lot of turbulent eddies. But we are not interested in the movement of the whole system, but only we are only interested in the vertical motion upwards and downward inside this mean wind field. So we subtract it, and as you can see in this formula, the deviation of the vertical wind times the deviation of something else you measure, like the number concentration, over a period of time. The mean, if it's positive, you have an upward flux. We define it positive flux, and if it's negative, so you have more particles going down than upward in this mean period, we say it's a downward flux or call it negative flux. Yes. So to show you a little example from 12 cases we had. In blue, we have the ice number concentration of particles larger than 50 micrometers, and in green of particles smaller than 50 micrometers. And the reason we chose 50 micrometers is that this is a good threshold to distinguish between water droplets and ice particles. We also can identify ice particles smaller than 50 micrometers, but it's very hard to do it in an automatic fashion. So we have to choose a threshold, and I chose 50 micrometers. So if we lower this threshold, this time series of ice number concentration will only increase. So that would be an effect. So as we can see, we have 3 steps in ice number concentration of ice particles. And then at the end of the case, a decrease of it again. And similar, we have an increase of liquid water droplets and a decrease again at the end. And just to show you that the fluxes I'm going to show on the next slide are not coming from a change of the overall system, let's say a change in the wind speed or a change of the temperature. I also plotted the temperature in red on the bottom. And as you can see, as the event started, the temperature dropped to minus 16.5 degrees and stayed there over the whole, almost, it stayed there for the whole period, and the wind was changed slightly from 140 to 125 degrees, so there was no change of an air mass or anything. So if we use the theory of eddy covariance and calculate the fluxes, we can see that a time series like this, so we have again time on the x-axis, and the flux for particles larger than 50 micrometers per cubic meter per second on the y-axis. So we have kind of a lot of downward and upward fluxes, but one prominent upward flux here at around 9 p.m. and it's connected to this large increase of number concentrations from 9 until 11 p.m. And similar, we also see in this increase an upward flux, but it's only half the magnitude of this flux we can see here. Yeah, so in summary, I've also looked at other cases, and they all look a little bit similar. We have identified multiple periods of significant, and I mean fluxes of over 100,000 per square meter per second of positive and negative fluxes. And this could be, I say could because we are not sure yet, this could be a major source of a secondary ice process. But for the end of this project, or for the rest of the project, I want to characterize those periods of upward and downward directed fluxes in their particular composition. So if we have needles, plates, or whatever, and if they are linked or special to upward and downward fluxes. And with a picture of some nice ice particles we've measured after this dominant peak I've showed you, I'd like to end my talk, and thank you for your attention.